I have almost finished all the mathematical part for this spontaneous emission. So I just review them. So after this lecture, we have no mathematical stuff. Okay. So until now, I just summary the 3 frameworks to study the electromagnetics. Okay, it's not just spontaneous emission. I think this is very important. You should know this which situation the model will be built down, it cannot be used. Okay, I think that in nano-optics regime, I think the first very important model is the classical Maxwell equation. Okay, they have 2 situations, two conditions. The classical Maxwell equation is valid. You can use them. You can solve your problem using commercial software or by your homemade code. Okay. First, the EM light intensity is high. I mean, there's many photons, maybe thousands or hundreds of photons. Okay, there's many photons. The light intensity is high. Another is object size is large, typically larger than 10 nanometer. If larger than 10 nanometer, I think classical Maxwell equation is also can be is accurate. Okay, they have 2 conditions. So people just solve this curve equation. Okay, I just add this. Okay, you solve this curve equation. Okay. This is in a commercial software like Lumino FDTD, like a CST, like console. It just solve this curve equation or in time domain, in frequent domain. Okay. Another thing you should care about is boundary condition, or how to add the boundary condition for your program. Okay. For this periodic grating, for example, you should add the periodic boundary condition on the left and right hand side. Okay, the periodic boundary condition. But on the top and bottom, the EM wave can be radiated. Okay, go to far field, so you should add a radiation boundary condition. Okay, some situation you should use a perfect electrical conductor or perfect magnetic conductor condition. Okay, we also have some continuous boundary condition. I mean, tangential E field and the tangential H field are continuous across interface. Okay, this is all the stuff for the classical Maxwell equation. Okay, you can. I believe there's many commercial software can solve this, can help you to simulate your structure. Okay.
Why the light has to be high intensity in order to apply the Maxwell?
Okay, I'll talk about it later. Why light intensity? Okay. Maybe third part. Okay, this is the most difficult. I just give you a concept. Okay, the mathematics is too difficult. Okay, but the second framework is called a semi-classical framework. Okay, this is just classical Maxwell equation plus some quantum mechanical Schrodinger equation. Okay, they have 2 situations. One situation, light intensity is still high, okay, but object size is small. I mean, smaller than 10 nanometer. Okay, consider a problem. This is a silicon wafer. This is a silicon. Okay, this is some silicon wafer.
Yeah, more size, right?
Maybe some silicon or GS, no problem. Maybe some. Okay, if I introduce some defect, it's very clean. Okay, this is I introduce some defect here, a small defect. This defect are isolated. Okay, I mean only have one defect. Only can introduce another defect, but they are isolated. It's important. Okay. Every material is from a microscopic view. There's many dipoles, okay, many atoms. If they are compact, if they are very close to each other, like a homogeneous object, we can use effective. You can use permittivity and permeability. Okay, we can use permittivity, permeability. Use Lorentz model, Joule model. Use some experimental tabulate. Okay, dielectric constant. We can model them. But if this object is quite small, like we introduce a very small defect, okay, they're isolated, or some quantum dot, okay, or some quantum dot, maybe. Some quantum dot, okay, they're isolated, okay, just one. I mean, you can have many quantum dots, but they are isolated. You put them very dense, you maybe can use classical EM, okay. This is a key issue, okay. So at this situation, how to capture this structure, okay? Because it's smaller than 10 nanometer, no permittivity, no permeability concept, okay? Because it's quite small. Okay? So here we just solve this 2 set of equations. The first equation is still a Maxwell equation, okay? But they use vector potential. I said in the quantum regime, people use vector potential in Coulomb gauge, okay? So the first equation you can see that it's just delta cross H equals to J plus partial D, partial T. Okay, it's just delta cross H because this is B over mu 0 to the h. So delta cross h equal to pi to d pi to t and plus j. Okay. But here j, they have two kinds of j. First j is for incident wave to source. Okay. And we add a j, they have some plane wave go here. Okay. This is a classical EM. But Q here is a quantum current. Okay. It's an influence of this atom quantum dot to this Maxwell equation. This is from quantum current. Okay, another equation just E. Okay, this here just E. Okay, just minus E equal to partial A partial T. Okay, so this is the Maxwell equation. And you use vector potential. Another just we use Schrodinger equation. Okay, Schrodinger equation you can see here is not traditional Schrodinger equation because I add QA in here. This is A just influence or EM to this atom. I means if you add a incident source, it produces EM field, okay? It produces a vector potential A. The vector potential A is similar to a force. We can make this electron in the atom a molecular motion, okay? This motion equation satisfies Schrodinger equation, okay? The P here is operator, is called canonical momentum, okay? It's a minus h bar delta. This is a Schrodinger equation, okay? When electron motion, they are polarized, right? They are polarized. They polarize, they produce a quantum current. They produce a quantum current. This is expression. This quantum current will modify the EM field. Okay, so this process is self-consistent. It's self-consistent. I mean they are coupled. They're coupled. Okay, this is a second regime. They call it semi-classical framework. Okay, in semi-classical framework, okay, I think the important thing is it's a Bloch sphere concept. Okay, it's Bloch sphere concept. Okay, we consider two-level system. Okay, excited state and ground state. Okay, I mean the total wave function is a superposition of ground state and excited state. The A here, you know, I mean the A and B is a coefficient. It means the atom has an A square probability at the ground state and B square probability at the excited state. And A square plus B square equal to 1. Okay, it should be equal to 1 and T equal to 0. Initial condition. Okay, initial condition. So we can define some polarization vector. Okay, polarization vector. You can verify this is satisfy this equation initially. I mean the polarization vector should be on the surface. On the surface. Okay. So why Bloch sphere is important? Okay, if no decay channel, okay, no any decay channel, I means the E field, if the E field is constant, or there's an isolated quantum system, their motion only on the surface, only on the surface of the sphere. Okay. But if it has some relative decay or other chemical reason relative decay, they is not on the surface of the sphere, but within the sphere. Okay, within the sphere. Okay. So you can see this is an example. Okay, I just show this example. Okay, if no decay channel, I mean no relative decay, you can here. So this point is 0, 0, 1 or 2. You can see this is if A equal to 1, sorry, if B equal to 1, A equal to 0, you can check Px equal to 0, Py equal to 0, B equal to 1, A equal to 0, the Pz equal to 0.5. It's this point. Okay. This is excited state, a totally excited state. This is a totally ground state. Okay. So here the motion, I mean the Rabi oscillation. This is the Rabi oscillation. I mean the atom will absorb EM wave from the ground state to excited state. Then they emit the photon from excited state to ground state. This process will repeat it. Okay, likely this circle will go around. Okay, that blue one. Okay. But if we have the relative decay or other chemical reason decay, you can see this curve will go down to the ground state very quickly. Okay, this is within this sphere. It's not on this sphere. Okay, so this from Bloch sphere you can see all the physics. Okay, all the physics. Because this part is a little bit difficult. Okay, a little bit difficult. So, but I hope you can know this. What's the meaning of this kind of equation? Okay, because you have here why self-consistent is important. Because this quantum current, because electron motion, right? Electron motion satisfies Schrodinger equations. It produces quantum current. This quantum current also modifies the E field here. Okay, this is a physical origin of the relative decay. Okay, this is a physical origin of relative decay. Okay.
So you can see that the wave function can describe it in this set of Maxwell equations. You can see the wave function there.
Yeah.
But in the lower part,
besides
the
this
No, this is not the wave function is the eigenfunction.
Yeah.
You say that already. The wave function is there, right?
Yeah.
This is from the Schrodinger equation as well as I guess that is the wave function that you describe. I mean the quantum properties.
Yeah, this is a quantum.
Electromagnetic wave is the y and a, right?
Right, exactly.
And if you go to next slide.
Next slide.
Next slide you have the px, py.
Oh, this is a fully atom motion. Like
this is
right, fully atom motion.
They all the governing this motion.
Motion equation. This is just this equation. Just solve these two set of equations simultaneously. Okay. When you solve this phi, the phi is a total phi.
Yeah, that's fine. Phi is I have no question about phi. But the px, py, pz, the governing properties. If you say the Schrodinger, the Maxwell equation govern this py, px, pz,
yeah,
we don't see them in these two set of equations. There's no.
No. You can see here. I just give an example. I just from this equation, I only can solve this.
Yeah, that's the one.
Right. I only can solve this.
Yeah,
right. This is a G and E.
This is phi and
right. This is eigenstate for ground and inside. If I can solve this, okay, they are orthogonal to each other. I can solve A and T. Right? They are orthogonal to each other. If I solve this, I can define Px, Py, and Pz. I define this. Okay, I define this. This is a physical meaning. Here we call it population inversion. Okay, like a laser. If they can go to a 0.5 or minus 0.5. Okay, they can Pz and Px, Py we call it transverse. It's transverse polarization. Okay, add them together, they satisfy this equation initially. Okay, but now every step we can solve the A and the B. You can solve them because they are orthogonal. I just test the phi G. There's 0 because orthogonal. Okay, so I can get the A. I test the phi E. I can get this B. Okay, so I solve this. I just can get this P and Py, Pz. I draw a motion. I draw this time motion. Okay, so this time motion just gives us information like a blue curve. Okay, they means they can from ground state to excited state, and from excited state to ground state. Okay, so this is similar to Rabi observation, similar to laser. Okay, like a stimulated emission, absorber photon, emission photon. Here it's just decay. Okay, decay to ground state because they have some relative channel or other decay channel. Okay, so this is
the 3D sphere picture that
you call block sphere.
Yeah, you have the ground state and the excited state in the with their coordinates, right?
This
and the question for me is that the
motion,
the whole picture, yeah.
Yeah.
How can you? What is X, Y, Z called? The physical meaning.
Okay. So typically PZ here is the polarization inversion.
That's
right. But PXY they call it polarization. Okay. This is a vector. It's similar to polarization. So what's the physical meaning here? It's my understanding. What's the because you can see this curve, this is sine omega t and the cosine omega t. So from my understanding, I'm not quite sure what's exactly physical meaning in here. But add them together, you can verify it's just equal to 1 or half.
Always.
Not always. If no relative channel, no decay channel, no decay channel. You can say if no decay channel, if this condition is initially satisfied. If initially satisfied a squared, b squared equal to 1, you add them together just equal to 1 or 2. Okay, it initially satisfies this. If no relative channel, like Rabi oscillation, okay, it's from ground state to excited to ground state, no relative channel, they always on the surface, okay, equal to 1 or 2. But if you have a relative channel, I mean, they will relate energy into free space or some other chemical reason will cause the relative decay, they will go to a ground state very quickly. Okay, the curve within this sphere. I just show this figure. So this is you can see this figure. You can see this is a phenomenologically defacing. Okay, we call it defacing. You can see this go down. Okay. Here you can see this is a red curve. It's a Rabi oscillation. this curve is a detuning case. I mean, the incident wave is not meshed with the transition frequency. But it's every curve on the sphere. Okay, so this has a little bit.
No, even the red one is also on the circle, on the sphere.
Yeah, on the sphere. But the yellow one, the green one, the blue one, all of them on the sphere. Yeah. But this is tuning, we call detuning. Okay, I mean tuning is incident wave is meshed to the transition frequency. Okay, this incident wave is not meshed with the transition frequency. So it's on the sphere, but we have no radiative channel. The wave out of radiative decay is important. Okay, I mean the perfect cavity. Okay, perfect cavity. The emitted photon go back. Okay, no radiative channel. Okay, so this is the case. Okay. But if we have radiative channel, it's not on the sphere. Okay. So this is okay. Because
so wave be also not radiative channel.
Cavity, closed cavity.
Closed cavity.
Yeah, PEC, no radiative channel. Yeah, EM they cannot radiate out, so it has some this kind of motion.
So what is the meaning of tuning and detuning?
Oh, tuning and detuning. Tuning means incident wave just mesh to the transition frequency. Okay, I mean you can see here. Think of cavity. Cavity has some resonant frequency omega c. They have transition frequency omega, and they are mesh. Okay, they are mesh each other. Okay, they call it radial. They have the radial very perfect. When they are mesh, they can go to the one. I mean, from this picture, if they are just mesh, I mean, because it's a cavity frequency, okay, just a mesh, the transition frequency, they can from the ground state go to this peak. This is a highly, it's called a fully excited state. It's not mesh. They cannot here, but cannot something here. Okay, called tube case. So all the situation just blocks the field. Okay, it's everything in the blocks the field. So block sphere is physicists they use this figure to show its experimental results, their theoretical results. Every motion is a block sphere, so they can see the physics quite well. Okay, it's on the sphere, off the sphere. What's the channel? This atomic motion, everything here.
But you say that a squared plus b squared equal to 1. That is the. That's okay. I mean,
t equal to 0.
But
okay, initially.
But does mean that if you did the time is not equal to 0,
because they're EM, they are self-consistent coupling each other. This only can produce called radiative decay. Other decay we must add phenomenically or empirically. Phenomenologically decay. Okay. This equation cannot capture. You just add them.
So this at the time of 0, this whole I'm okay with the understanding of this, but can it be not 0 equal to 1?
What's that again?
Can it be not equal to 1? I mean, but not time. The a squared plus b squared, can it be not equal to 0?
Right. Yes. Can.
And what
situation? Here they have radiative decay or other decay. If I have radiative decay or other decay, they are not equal to 1. Okay. So it's not on the sphere, but within the sphere. Okay. This is the case.
So if that's the case, how people will describe the case? I mean, when you say
phenomenal decay. Just add a decay constant arbitrary, empirical. No governing. Okay. This is a semi-classical. But radiative decay can be captured by the self-consistently solve the Maxwell equation and Schrodinger equation. This part we can capture. So this is the second. The third is called quantum electrodynamic approach. Just why need an approach? So object size is still smaller than 10 nanometer, but light intensity is also small. This is very important. Okay, in the semi-classical and the classical, the light intensity is strong. I mean, they have many photons. Okay, if they have many photons, they form EM wave. The EM wave can interference with each other. They call interference physics. Assume that only has one photon. The one photon is similar to a particle, no interference. It's similar to particle. They have shown some particle feature. The loose interference feature. Okay, they cannot use the classical EM. They not interference in the classical EM. Only have 2 or 1, 2, 3. It's a particle, right? It's not waves. They cannot say that here it's just waves. Okay.
But yes, it's a wave. But interference one thing. But from what you said, is interference must be there in order to have
the interference cannot
describe
interference is cannot similar to classical wave. Okay, so they're similar to show some particle feature. Or at least it shows some particle wave duality feature, very strongly. Okay, very strongly. It shows this feature. I'll tell this later. Okay. So you can see here what's the governing equation. Everything is same. Okay, this is a Maxwell equation. Okay, this is a Maxwell equation. This is a Schrodinger equation. This is Schrodinger equation. But you can see only difference is I changed the Maxwell equation with operator form. A, Y is an operator, is an operator, is an operator. You can see what's the physical meaning, because I did not talk about how to derive this because it's too complicated. But the physical meaning is very interesting. They said, okay, E field or A field can be superposition with eigenmode. Here is eigenmode. Okay, this eigenmode still classical eigenmode. It's a classical feature. This is wave physics. They capture in wave physics here. But they have operator AQ and AQ plus. They call it correlation. They call it correlation and annihilation operator. They capture a particle. Okay, particle nature. So this here is a wave particle duality. The wave particle duality. Okay.
Does it relate to the Schrodinger?
No, this part cannot relate to Schrodinger.
No, okay. I mean the A and Q.
Then you can see A here. Originally in semi-classical, A is a classical field. But here the A is this operator. Okay, this operator. So you can see here. Everything is same, but A and Y, all the field are operator.
But the power is small AQ.
What's a small AQ? This here?
No. In the equation.
What's the equation?
Correlations or operator?
Oh, this here. This is operator.
I'm not saying that it's not operator. This operator actually, let me see.
This is some expression, you know. What's the physical meaning? If this operator do this wave function, okay? If this wave function has two parts, electron part and the EM part. If they add the EM part, because this is the EM creation and annihilation operator. If this part add 0 photon, they become 1 photon. Okay. This has physical meaning. This is creation photon, this annihilation 1 photon. Okay. So this is just particle nature, just increase. Okay, this is a so it's a picture. So finally, when you quantize EM field, so not difficult. Everything become a harmonic oscillator. The Q is eigenmode. So what's the final picture for quantized version of electromagnetics? They said every eigenmode as LC circuit. Okay, each eigenmode like LC circuit, but the L and C is equal to quantized version. Okay, the mode 1, mode 2, mode 3. When you solve each mode, when you solve this harmonic oscillator model, you will find that this is the important thing that when you found that the ground, this is the anti level, okay, similar to black body radiation, okay. The ground level is h bar omega O2, we call it zero fluctuation. This is a physical origin or spontaneous emission. This is a physical origin or spontaneous emission, okay. This is a physical origin or spontaneous emission. So the idea is here. The EM energy, total EM energy can be represent the superposition over energy of each eigenmode. Okay, like each eigenmode I use quantized version. Okay, I saw this quantized version, quantum harmonic oscillator version. I can get this eigenstate. I get this eigenstate. Okay, the ground state is just called zero fluctuation. Okay, this is a physical origin or spontaneous emission. I finished all the part. Okay, so. Let me summarize what's the physical origin of the spontaneous emission. Okay, when the dipole emit photon to a free space, okay, they also absorb energy to free space, okay, or from vacuum. Okay, from classical theory, the vacuum has no EM field equal to 0, but it's not right. From quantum mechanics view, the average value or interpretation value of E field equal to 0. But E square is not equal to 0. Okay. All apart. I think if you cannot mathematics.
Let me ask you one more question.
Okay.
I think that is something that we still have to know.
Okay.
In your concept, there's one thing that is very important is the space. I mean the size.
Okay.
The
size. The size.
Why it becomes important is that when the size reduces,
yes,
it's smaller than the ball radius. that you start to have some confinement. Therefore, you have to introduce, we have to introduce quantum mechanics behaviors.
Yes.
Therefore, we have the quantum properties set up. Therefore, we have to solve these Schrodinger equations for understanding physics.
Yes.
And therefore, if we want to study the wave properties, the EM wave, we have to have the semi-classic. That is the reason why we handle the Maxwell equation together with the equation for the whole concept, right?
Yes.
But in one situation, it doesn't include it here is that, well, if the emission is we don't have this limitation, it's a bulk, the material is bulk, we don't have the limitation of the small size, no quantum effects. That is totally
This is a very good question. If we have bulk, right, bulk material, but if you put this bulk material in vacuum, I mean in a very dark environment, the Maxwell equation still need to be quantized. Okay, still need to quantize. Otherwise, you cannot capture, right? You cannot, understand it. In a dark environment, there's no photon in classical. But here, this bulk material still spontaneously emit photon. Okay, so typically we only, solve this problem as a, one atom and I put them superposition. It's very difficult to solve.
Can you go back to the first case?
Okay. Okay. The light intensity is high.
No. I'm saying don't worry. It's too far to give me the answer. If you go to the first question, first case, it's the case that your size is big. First case, not the third case.
Sir?
First case.
What's the first case?
第一个.
This first case?
第一个. Okay.
This classical.
This is the first case, right?
Yeah.
Size is big.
Yes, size is big.
And the light has to be have high intensity.
Yeah, high intensity.
My concern is if we don't have high intensity, but the size still big.
Yeah. So I tell you that you should quantize Maxwell equation. No choice. Think about this is in dark environment, no photon. This bulk material maybe spontaneously emitted photon. How to solve this problem? It's very difficult. Very difficult to solve this problem. Why? Because it's very large. Because for EM part, it's very large. The many atom. Okay, the many atom. Only now, with our capability, only can solve thousands atom. If you quantum mechanics approach, it's not easy. But EM, you have no choice, right? How to understand spontaneous emission? If in a vacuum, if dark, no photon.
The point is that in EM wave, people don't. The first starting point is that assume you have a dipole. Assume you have a assume you have a dipole. You already can start the story to tell people. But whenever you
rigorously, you should do that. But they have some.
Is that right? I mean, that's my point, right? Okay, I have a system.
Yeah.
Assume I have dipole there. Then I can, the dipole is an EM wave. I mean, the source of the EM wave.
Yes.
Then you can use Maxwell equation to tell the story. But now you tell us that if in here I have dipole.
Yeah.
But you say that no. If the size is big and we don't have many dipoles. Then
we have many. So first thing.
I didn't at the beginning when people even in LED.
In LED. The importance of LED is quite different. You should add bias. Okay. I call spontaneous emission. You know this concept. This is called no voltage, no anything, just in dark environment, in vacuum, you put some atom with spontaneous emitted photon. Okay. Even in fog, it's spontaneous emitted photon. In a very dark environment, it's still emitted photons. So what's the original EM field? Because no EM field.
You have the dipole.
Right.
But you have the dipole.
Right.
Dipole, right?
Right. They have dipole, many dipole, but what's the EM wave? The EM wave are vacuum fluctuation. Okay. It's a vacuum fluctuation. It's just ground state of this quantum harmonic oscillator. Okay, so that's the meaning of why I quantize. Okay. This is the EM wave. This is 0 point energy. That means even temperature go to 0, T go to 0, even in very dark environment, here still here. Okay.
So this is the picture that we should also consider in the first case.
Right.
第一个条件你还是要考虑这个。
Yes. If the but this is very difficult. It's very difficult. Why? Because it's a bulk material. Atom coupling very strong. Right? Many atom coupling each other.
But then what is the requirement for considering this concept?
Okay, this concept, no photon. In vacuum, no photon. In dark, only has few photons, 1 or 2, 3.
In vacuum, but in vacuum without a material there.
No. If you have a material, you also should use this. Okay, but eigenmode change. Okay. Eigenmode change. This is important. You can see this EM field. In vacuum, or put some material, everything is same, but here UQ is not same. Eigenmode change. In free space, it has eigenmode, right? I put on bulk material, eigenmode change. So it's and E.
So the first case is in vacuum or in free space?
If in free space or in homogeneous space, it has incident source. It's very important. It has incident source. Okay, a laser source, LED source, and maybe EM, they have antenna, they have source.
So when you say in vacuum means we don't have any source?
Yeah. In vacuum, in dark environment, what's the source? In vacuum fluctuation. You only have vacuum fluctuation. Okay. This is source.
But in the sky it's vacuum, but we have sun.
Yeah, that's a very good question. It's classical. Solar cell is fully classical, yeah. They have sun, right? I think a vacuum is not sky. Vacuum is some very close environment without.
So the sun is like, you can see.
Right, sun is a classical EM.
Okay. I'm not saying that sun is not classical, but point is okay.
So I have no time because I have to move forward.
You have to keep the
right because I have to move forward for my lecture. I cannot discuss too much here. Because I have finished all this part, let me talk about this spontaneous emission. Okay, for this spontaneous emission, we have two concepts. One is the local density state, one is the density state. Okay, so density state just count electromagnetic mode per unit frequency. Okay, so local density state just count electromagnetic mode at a physical position. Okay, at a physical position. Okay, it's similar to a spatial redistribution of density state. The spontaneous emission only depends on what we call a local density state. It's a local density state of a state. Okay. So I give this concept. Okay, but no mathematical equation, just fully concept. One concept we call a Purcell effect. Okay. So Purcell effect said, okay, spontaneous emission of atom can be modified by the inhomogeneous electromagnetic environment. Okay. That means in vacuum, you put some atom in a vacuum, it has spontaneous emission rate. But if I put an atom around a metallic sphere, around some object, the spontaneous emission rate can be modified. Okay. This is called a Purcell effect. Okay. For a resonance cavity, the Purcell factor can be proportional to a Q over V. The Q here is called a quality factor. Okay, quality factor. And V we call a mode volume. Okay, you can see this expression. For a cavity, if the EM wave is very focused, in a small volume, here the V becomes very small. You can see this is maximum value. Okay, this is average value. If a focused EM wave is very small region, the V becomes very small, so spontaneous emission can become very large. They call it Purcell factor. Okay, for large Purcell factor, we have large local density space, we can large spontaneous emission. And
the radiation time will reduce, right?
What's the time?
The
decay rate will increase. Okay, will increase. We will increase the lifetime.
Right.
Lifetime will be short. Yeah. This is okay. So this is my work. This is not my work. First also is a Charpon phase work. Okay. You may think my lecture is very difficult, so I just show this paper to you. Show this paper to you. Why I show this paper? Because this paper, the first author is undergraduate student. In our department, professional. Now he obtained PhD degree in UIOC. At that time, he worked with Troy, me, and True, right? I guide him to finish his work. He's undergraduate student. You can see his equation first, right? This is spontaneous emission. It has an eigenmode. It's a green function. Okay, fully quantum mechanical. Then they derive some analytical solution. Okay, analytical solution. They use a finite difference method. Okay, I teach this finite. Everything is done by him. Okay, the generation all the figure. Okay, the power paper in physical review A. Okay, that's good. Right, this is very good. This is undergraduate student. Why he can do that? Because initially he found it very difficult. He cannot understand. But I tell him you can try. No problem, you can try. But finally he finished his work. Okay. So sometimes students are still by yourself. Because I'm an experimental researcher, I cannot understand this equation. Because you did not spend time. Okay? When I spend time, I solve everything. This is just undervalued student. So I think this is an issue. Okay? So I just see this history result. Okay, it's a photonic crystal. It do a photonic crystal, it do a plasmonics. Okay, one pair it do a photonic crystal to a plasmonics. So you can see the photonic crystal structure, the dispersion relation. You can see at the band gap. At the band gap, this spontaneous emission, okay, very small. This normalized spontaneous emission, I mean similar to Purcell factor. Okay, this is spontaneous emission in homogeneous environment over the spontaneous emission in free space. Okay, we call it normalized. Here, very small. You can see 10 over minus 6, very small band gap. Okay, in band edge or something, they can boost. Okay, they can boost. Okay, you can see a TM wave and TE wave are quite different. Okay, in TM wave, almost is 10 over 0. So almost not changed so much, but for TE wave, we can enhance 100 times. Okay, this is TE wave. This is interesting thing. Okay. But for TM wave, we consider a dielectric cylinder in air. For TM wave, we consider the hole, air hole in a dielectric matrix. Okay, everyone know that they have band gap for TM wave. This have a band gap in TE wave. Okay, so band gap and the band gap has no photon state. So the local density state become very small. Spontaneity become very small. Okay, and the band edge can boost. Okay, this is a picture. Another is about plasmonics. I put the diagram here for plasmonics. Okay, you can see here. If I reduce the distance, between the two plates. You can see the double plate case, the spontaneous emission can enhance very quickly. Here, you can see enhance very quickly for spontaneous emission. Because very small, they can inside the surface plasma. The surface plasma can interact with each other.
Do you see fan resonance in this case?
No fan resonance.
Why? Because this structure is not symmetric.
Oh no. Sorry, maybe I confused that. This is a double. This is I just two cases. Two cases. Okay, two cases. You can see this is one case. It also enhanced the compared to this is smaller. Okay, this is plasmonic enhancement. You can see different dipole show different pattern. Okay, so spontaneous emission depend on local density state. The local density state. What's the local density state? The local density state, the LDOS just in proportion to the imaginary part trace green function. The trace green function just gxx plus gyy plus gzz. Okay. So this is a trace. This is the LDOS. So you can see that different dipole have different contribution. Okay. If Z polarized, if Y polarized, it's symmetrical. You can see the mode is symmetric. It's X polarized, it's asymmetrical, similar to asymmetrical. Okay, they can excite the surface plasma. You can see the high intensity. But here, if I go for Z direction, because it's polarized on Z direction, okay, no, you cannot excite the surface plasma because no surface charge. It's no surface charge. So this part of contribution equal, strongly smaller. Okay, this is for the LDOS from surface plasma. Okay, this is for LED. Okay, for LED. I just show some video if I have time. Show LED. Okay. Show some video. Let me. Okay. I found out this video is good. I found in the YouTube. Okay. That's interesting. What is this? Oh, it's make something wrong. It's called LED and OLED.
What we have here is light-emitting diodes, LEDs, and what they are, they're a semiconductor. The diode conducts electricity only one direction, and it stops it the other way. So if you feed it with alternating current, it will change alternating current into direct current. And if you take a diode and you add various chemical compounds to it, not only will electricity go only one way, but it will emit light.
It's a history.
use something like silicon, which is a fourth group element, you have an indirect band gap. And so that indirect band gap means that the electron and the hole being the absence of an electron, when they come together to form the photon, they have to travel in an XY direction. So you're traveling off of a Y direction to get to the electron in the hole. And as a result, you get a release of heat as well as light. So you get more heat than you do light because of that phenomenon. Or you don't get as much light because you have a lot of other phenomena going on. So that's why they use 3-5 materials like gallium arsenide to get that light output. And you're limited to those materials to get that effect. And so when you use OLEDs, the difference is that you can use any substrate and you use organic materials, which is where the light emission process actually occurs. And as a result, that allows for a lot more flexibility in terms of the different materials or devices you can use.
Typically, we form an indium tin oxide layer, which is a transparent conductive material, very commonly used in optoelectronic devices. That is sputtered onto the glass substrate, and on top of that, it's an ITO film. Then we form a stack of very thin organic material coatings, anywhere from 5 nanometers thick to about 200 nanometers, depending on your device construction. It can be anywhere from about 5 to 10 different coatings that we stack on top of each other. To make a white device, typically we form 3 emission layers, red, green, and blue. And the combined emission from those layers forms white light. And the emission layers, typically there's an electron transport layer, and the cathode acts to inject electrons into the device. It's also a reflective material, which is very important. If it's not a reflective metal, a lot of the photons will be absorbed at that interface. In the off state, it's a mirror. Basically, you can see a reflection. What you're seeing is a reflection of the aluminum reflective cathode. The OLED materials are very efficient, and they can efficiently generate photons. We can create an OLED device that's about 30 to 40 lumens per watt efficacy without using any extraction technology. But the potential is there to get well over 100 lumens per watt if we can solve some of the problems with the light extraction.
Some inventor. I did not see the John Bardeen. John Bardeen should be here. I did not see the John Bardeen.
This is laser.
There's no John Bardeen.
No, I mean it's not LED, it's laser.
Oh, John Bardeen later?
No.
I see someone.
I see this is why they said
this guy.
And he cannot get the Nobel Prize. Yeah, he get the.
Yeah, that's yellow. It's a progress in this field. Oh, yeah. This is not verified. This is not verified. That's blue.
Probably also get the Nobel Prize, but not in LED.
Yes. So in this. This guy?
Yeah, he's nominated but not success. I guess he has no way now because.
I also see the Rachel Brand. You can see. I see the Rachel Brand name. Not see the later. Oh, it's Adachi.
Yes.
Adachi also is do something. To Japan. Yeah, Rachel Brand. I see his name.
But I guess.
Also, it has still progress in this field. Okay. This is an interesting video. Okay, so I almost finished. But silicon forest, they come from you, right?
Yeah. They all of them has been used.
Okay, so I just finish this part. So I just talk about this principle and I can finish this lecture. So what's the working principle for LED? LED has a lot of applications. So here is a PN junction. LED just is a PN junction. They can convert a solar light into the electric current. This is a solar cell. Okay. LED just reverse process. They just can emit light when you add a bias of when electrical energy is applied. Okay. So this is called electroluminescence. Luminescence. Okay. Electroluminescence. Okay. So here. The first picture is no applied voltage. It's no applied voltage. The P junction, N junction, when touch them together, that is a same Fermi level. Okay, the Fermi level will align. Okay, this is the first case. When you apply voltage, the P junction is this is the equilibrium state. Okay, an equilibrium state that has the same Fermi level. Okay, it's equilibrium state. But if applied voltage, okay, here it's applied voltage here. So electron hole has different Fermi level. Okay, electron hole has different Fermi level. We call it quality Fermi level. You can see this is a N type. This is a hole Fermi level. It close to this this is electron. This is N type. This is electron Fermi level. It's close to the conduction band at this N type. Then they go down to this P type side. Okay. For this quality Fermi level for this hole side, it's very close to this valence band at the P side. Then they drop down to this here. Okay, you can see they have distance, the quality Fermi level. This distance just around applied voltage. This distance just equal to applied voltage. If no applied voltage, the two Fermi level just align. Okay. If applied voltage, they will splitting. This is completing. Okay, here. So the gradient of quality Fermi level will driven the carrier. So what's the recombination region? Around here. Around here. Okay. It's around this depletion region. This depletion region. Why it has a gradient? You can see it has a gradient. This is a carbon picture. There's some gradient around here. There's some gradient. Okay. So the gradient of quality Fermi level is a field of original current. But what's the current? Just proportional to the gradient of quality Fermi level. Okay. So this is a picture. So they can recombine. They recombine emission light at this depletion region. So the electron from N type side and the hole from the P type side, then they recombine each other. They recombine each other and emit photons. Okay, around the depletion region. Around this depletion region. Okay, this is a working principle for LED. Okay, this is a working principle for LED. Okay, so why we should use a direct band gap? So in the lecture, in the video, we said typical did not use silicon. Silicon has indirect band gap. Okay. So silicon here, this is here. It's not aligned. Okay. This is band, conduction band, symmetry. They call indirect. Okay. So for do some transition from photon transition, this part it will be phonon. Okay. This part is similar to photon. This part is will be phonon. So when electron recombine with hole, it goes reverse process. Okay, they produce heat because phonon part. Okay, so the people just use 3 or 5 chemical. Okay, this direct band gap. This direct band gap. Direct band gap. This is okay. This is conduction band. This is valence band. So when the electron and the hole recombine, they emit a photon and that will produce a heat. Okay, that will produce heat. So this is part by the phonon part. So this is why people use direct band gap. So the emission light wavelength, if we see a two-level system, okay, if we see a two-level system, so the emission wavelength is around here. It's around the band gap. Okay, it's around the band gap. Okay. Okay. So you look different material like gallium arsenide, gallium nitride, you can use different color. Okay, this is a traditional LED. It's OLED. OLED because material reason, because organic material can bend. Okay, and flexible. Okay.
Also, it's a large area.
Large area, okay. You can also can large area. So this is a basic principle. Because our lecture is focused on EM and talk about too much about the semiconductor physics. Okay. So what's the main issue in LED? Light extraction. Okay. I mean many light are just become a guided wave. It cannot emit out. Okay. This is work by the Fan Hui and Yang Knowledge. Okay. Highly scientific. At that time, with a photonic crystal. Solve the issue. Okay. So what's the ideal LED? Ideal LED, we the pattern extraction become very high. Extraction high is to increase the density or radiation mode. Okay, because it can couple to full free space, couple to outside to increase the density of freeze mode, and decrease the density of guiding mode. Okay, if you inside the guiding mode, it will trap into a device, it cannot read out. Okay. So this is Okay, bulk. It's very simple model. It's bulk active material. This is a dispersion diagram. The gray region is the radiative mode. This fork curve is guided mode. Okay, they solve the dispersion relationship. Okay, then they calculate the output efficiency. Almost very small. You can see, very small. Okay, only has a peak here. Okay, so what's the reason? So from my understanding, you can see here, the black one are symmetric. This mode are symmetric along the x or y plane. I assume that the z polarized dipole. Okay, so they can excite the black one, and this whole one. Okay, these two curves are unsymmetric x or y plane. They cannot excite by EM wave. Okay, so only the black one has a reason. You can see here is 0 because they are excited the guided mode. Maybe only has a jump. You can see it has a change in here. Okay, it has some. It's very high here. Okay, so it's a reference here. Maybe here the guided mode become weaker. Okay, then I go to this guided mode. Okay, it becomes smaller. You can see this output efficiency is very small because they excite guided mode. They trap. I mean, they trap the EM energy in this layer. This is a slab. Okay, this is a diode. Okay, they trap energy. Okay, this is even less. Okay, they trap some guided mode. Okay. They cannot emit out. So what's the fancy idea? The very simple idea. They use photonic crystal. Okay, with many holes. With many holes here. Okay. So so along the x or y plane, this is a band gap. This is a band gap. They cannot couple to this guided mode, but they only can emit out along z plane. So this is the band structure. Okay. See the band structure very clear. The gray region are radiation mode. And this curve are guided mode. Only has this small region has guided mode. You can see the guided mode was only has small region. So you can see here, around this region, the fully radiation mode will become very high. Okay, the output efficiency reaches to the 80%, and reaches to 80%. Okay, so the very strong emission because along x or y this is a band gap, so they only can emit along z. Okay, they are stopped along x or y plane. Okay, this is the band gap. So this is ideal. So this is experimental research. You can see this is electrode. The P and N is maybe injection layer. This is active region. Is quantum well. Sorry, it's so the light. You know, initially they are guided away. They are guided away, but from this photonic crystal, they couple to outside. You can see it's no photonic crystal. They have photonic crystal. It's a very strong light emission because at x or y plane, the band gap they can stop. They only can allow this direction emit. Okay, this is by this experimental realization. Okay, so thank you for giving my lecture. Okay.